tell me, whichever, one's higher, one's lower, the same, what's the deal? So Andrew says when it's straight, it's got higher potential energy. And your argument for that is? It takes less to get it to go to coiled, right? It takes a little tiny flick to get it to coiled, but it takes some serious work, well, sort of serious work, to straighten it out, all right? So it takes more energy to straighten it than to kink it, all right? How does, did you guys talk about stability? So what he said is this is a less stable state because it's far more likely that this thing is going to kink up on its own. Like, for example, if I just drop it, sometimes if you just drop it, or if you, well, that was a great demonstration, if you actually just touched it and it flipped, but it's almost never going to happen that you're never going to have it coiled and have it snap to straight. All right? And so that's right. So that was what I was after. So let me put these on the graph. Thank you, Andrew. So what we've got here, the straight state has the high potential energy, and the coily state has the lower potential energy. Right? And there are several different words to talk about this. This is unstable, relatively speaking, and this is stable. What I should really say is more stable, less stable, but that is unstable, it is likely to change, right? State, and this is unlikely. State, all right? Questions about that before we talk about, there's all sorts of cool stuff that comes from that, but just from there. Maybe everybody's with me on high potential energy, low potential energy, what's going on with that? Okay. So there's a couple things we can add about the transitions there. And I'm going to use different colors for these. So, actually, let me do the green one first. Green. So, we can talk about two different processes, this away and the reverse. This chain, and there's a couple things we can say about this. This thing, and actually let me draw the reverse reaction too. So, like most chemical, we're going to make an analogy to chemical reactions in a little bit, but like most chemical reactions, this turns out to be reversible. Some are more easily reversible than others, but you can actually go from one state to the other in either direction. So one of the mistakes people oftentimes make with graphs like these, they call them reaction coordinate diagrams, there's lots of different names for these things, is they think that this is a time axis. So you always go this way. Right? You go from long ago to now, or now into the future. The time moves this way. That's wrong. That's not. It's really important. This is more like a map than it is like a graph. It says that's lower energy and that's higher energy. So if I go this way, I'm going up in energy. That way, I'm going down. And I can go either way. Right? So it's not a time axis, which is really one of the important things to keep straight. All right. So let me say some things about what those lines mean. This reaction releases energy. That is the snap. You know that, right? If you whack it, you can actually get spanked by it if you do it wrong. It can actually hurt you. There's energy released. And you're turning the potential energy into kinetic energy, if you like. This is also would be called the favored reaction. It is more likely to happen. It is also spontaneous in a thermodynamic sense. And the energy of the bracelet decreases. So that means that the delta PE is negative. Right? So the potential energy, let me write that E really nice and neat, is negative. Right? So that is high potential energy, low potential energy. From the point of view of the bracelet, it has less potential energy. Energy is conserved. That energy goes into slapping my hand, making some noise, getting the environment a little bit warmer. But this is high potential energy, and this is lower potential energy. And that energy gets given off as heat or whatever. All right. Likewise, the reverse is true for all. The opposite of those things is true for the reverse reaction. So this thing, you must put energy in. How do you know that, right? Once it's coiled, it takes some work. You got to stretch it out, right? Well, I'm exaggerating, but okay, you got to stretch it out, right? So you got to put some energy in. Likewise, this is the unfavored reaction. It is non-spontaneous. Okay. And here the energy of the bracelet increases. So delta PE is positive as you go in that direction. Make sure I got all the pieces of that. So we're going to draw free energy diagrams like this of molecules, and that's what it's all about. It's the energy of the molecule. So when you talked about the TNT molecules, TNT is unstable. It's high energy, and the products of TNT exploding are down here, lower energy. And the difference in energy is given off as kaboom, right? The sound and heat and light and all of that comes out. Okay? Now so the products of the explosion are stable, TNT is unstable. So it's the same sort of thing as this, right? Questions about that before we talk about it? There's a very important detail I have left out. Okay. That is the following. Question. If going from straight to coily is favored, why doesn't it snap in your hand? Right? So, sure, I'm saying that this is unstable. Right? It really kind of, in our wanting way, it wants to be coiled. Why doesn't it coil? How come I can keep it there for as long as I like? It's not going to coil. Why doesn't it coil? Or what does it need to do? What do you need to do to get it to snap? Yeah. It needs another force. And what exactly do you have to do to get it to snap? What's the trick? Yeah. You put a little bit of energy into it. Specifically, even we're not talking just talking physically. What do you do? What do you got to do to get it to snap? You agitate, or even I'm fishing. I know. Here we go. What I'm after, which is true of all these things, is you have to kink it. You have to put a little pinch in it. Once you start it bending, right? Here it is, this unstable state. What I do is I put a little kink in it, and once you put a little kink in it, the whole thing snaps. If you feel so, like if you pinch it between your fingers like this. You can't see with my fingers, but I'm basically going like that to it. You'll find it goes boink and snaps. All right, so you got to put a little kink in it. Yeah, and exactly, you got to put a little bit of energy into it. So my question is the following. So you need to put a kink in it. All right, you got to start it off. So, therefore, there's a third transient state. What do I mean by transient? You cannot keep it in that kink state. It will snap on you, right? It only stays in that kink state for a split second, all right? So that's what I mean by transient. All right, it's a third transient state. We'll call it kinked. And I'll draw it as that sort of shape. So where on the chart? All right. So my question is to talk to your neighbor about, I'm going to redraw this chart with the straight and the coily. Where does kinked go on that chart? And not only left to right, but up and down. Given what we've said about how these diagrams work, and given what we said about putting some energy in to put that little bit of a kink in it, where does it belong on that chart? So while you guys are talking, I'll redraw the chart.